And now comes the time we've all been waiting for, example problems from section 4.6. So this would be related to tangent, cotangent, cosecant, and secant. So the first thing we're going to do is, this is just an example, where we're asked to find the x-intercepts, the y-intercepts, and the intervals where the graph is increasing, and so on and so on and so on. All right, so this is for cotangent. So we got this nice graph of cotangent. Now we know that it's exhibiting asymptotic behavior here, here, and here, and it's equal to 0 here and here. Now you can read it off the graph or otherwise, but this is at pi over 2, 3 pi over 2, this is pi radians, right? 0, negative pi, right? So they're repeating with some regularity here. Negative pi over 2, can't help myself, negative 3 pi over 2, and so on, right? So x-intercepts. So here's how we'd write this. So the x-intercepts would be at x equal to pi over 2n, where n is an odd number. Meaning, if it was equal to 1, it'd be pi over 2 times 1, pi over 2. If it was equal to 3, which is the next odd number, it'd be 3 times pi over 2, or 3 pi over 2. Or 5, which would be 5 pi over 2, and so on. And it can also go negative. So this is kind of a cheat way of not having to list them all off. Though if you wanted to, I suppose within this realm you could. You could just list off these 4 values within this viewing window. Y-intercepts is an asymptote. So in this particular case, there is no y-intercept for cotangent because it's an asymptote. Intervals in which the graph is increasing, this graph is going down from left to right, right? Which means it is never increasing. For D. So technically what's happening, wherever the graph is defined, remember asymptotes are like skips in the graph, but wherever the graph is defined, it is always decreasing. Oops, I should have answered that as part of C also. So it's never increasing, but is always decreasing. If you think about it carefully, tangent's always increasing, right? So this is D. Let's get rid of this. Get rid of the evidence, right? Find all relative extrema. Remember, maxes or mins are what the extrema are, so there are none in this particular case. E, all vertical asymptotes. So we can sneak this in here that the vertical asymptotes are always going to be x equals, but they're going to equal to what? Pi n, where n is even. Okay, you could just list them off, negative pi, 0, and pi, or you could say, hey, it's going to happen at pi n, meaning pi times 1, or pi times 0, or pi times negative 1, or pi times negative 2, or you get the picture, right? So this is kind of a little, not cheat per se, but a way of covering all our bases all at once, right? Okay, so this next is sketch the graph of a function, include 2 full periods, and then use graphing utility to verify your results. Okay, so this is tangent pi x. So this pi is going to affect the period. So we know the period, that's our b, right, is equal to pi, because it's tangent, right, over pi, which means the period is equal to 1. So if we remember way back to when, our basic tangent graph is, now this hasn't been shifted left or right, it has been vertically stretched though. So what's happening then is the period, that is the space between these lines, is going to be equal to 1. So tangent, remember, is equal to 0 at 0, right? Which means at 1, it's going to be equal to 0 again. And at 2, it's going to be equal to 0 again. And negative 1, it's going to be equal to 0. And negative 2, it's going to be equal to 0. Let me use a different color for the actual graph. There, and there, and there, and there, and there. Now we know that it's going to go up from left to right, right? And it's going to have asymptotes. And where are the asymptotes going to be? They're going to be halfway between here. So at 0.5, right? 1.5, 2.5. So they're going to happen every one also, right? And then the actual graph. Now this is where it gets a little bit tricky. The 1/2 makes this slightly lower. In reality, because you're sketching it, you're not going to be able to tell the difference, really, okay? So you're going to see this same pattern. The biggest thing that you're going to notice is the period. which has changed. So instead of being every pi radians, aka about 3.14, pi is equal to 3.14, right? It's going to be happening every 1, okay? So that would be the sketch. Okay, cosecant. Well, think, I'm being serious here when I say think sine 2x minus pi. Your best bet is to go ahead and graph sine 2x minus pi. So remember, when you do that, you have to factor this out to figure out what the shift is, because there is a horizontal shift here. 2x minus pi, when you pull that out, it becomes x minus pi over 2, right? What is the period? The period is equal to 2 pi over whatever b is, so 2, so it's every pi, okay? Now, as a little bit of a way of making this symmetrical, I know that this thing is going to be a sine model that's going to repeat itself every pi radian, so it's going to look like that, right? And it's going to look like that. That's what the basic sine model is. Now it has an amplitude of 1, right? So this is negative 1 and 1, right? And we can label some points. We know that this is pi. This is pi over 2, right? And this must be, well, you divide it into fourths. So that's pi over 4. And this would be 3 pi over 4, if you want to get particular, right? So remember, you're actually graphing cosecant. So what I've done is I've graphed sine of this exact same thing, right? And now what I'm going to do is, wherever it's equal to 0, I'm going to draw in a vertical asymptote. That's when it's undefined. And wherever there's a min or a max, that's going to be a point on the graph, and it's going to have a little cup, just like that. You can even leave the sign on there. Why bother erasing, right? You're just going to mess something up. And this is a sketch after all, but there it is. That would be 2 periods of worth of cosecant. So I graph the sine first, and then graph the cosecant based on that. Okay, so use a graphing material, so graph the corresponding reciprocal function in the same window. So this and this are virtually the same thing. So what I'm going to do is I'm actually going to graph, remember I had to pull the 2 out. I did that before. So remember, when you're doing that, so I distribute 2 times x, 2x, 2 times pi over 2 divided by 2, that cancels, I get minus pi, right? So what happens is I still end up with, let's graph sine in red. You know what, let's make our axes a different color. So we'll make the axes this. We're going to do this backwards, like I said. So we'll graph sine in red. And now, because I'm sketching this, what I can do is I can adjust this, so I know that this is 1/2, and this is negative 1/2. This hasn't been shifted up or down, so the midline's at 0, right? Amplitude is 1/2, so it's as high as 1/2 as low as negative 1/2. The period, as we already found out from the last one, right, period is equal to 2 pi divided by the multiple, which is 2, or pi radians, right? So this is pi over 2, 3 pi over 4, and pi over 4. Remember, it's divided into 4 equal pieces. Negative pi over 4, you get the picture, right? So, graph the corresponding reciprocal in the same window. So what we're going to do is now do exactly what we did. So this graph is going to be virtually identical to the last one we did, except that it's going to go, it's going to have maxima and minima, right? So we're going to do the cosecant in blue here. Are going to be slightly different, as in this is going as low as 1/2 or as high as negative 1/2 in each case. Right? So just like that. Okay? All right. Use a graph of the function to approximate the solution. So what I'm going to do is I'm going to graph this function in Desmos, and then I'm going to graph this function in Desmos and see where they intersect. Okay? This is what this would look like. So I need to pull up my appropriate graphing window. So this means that I'm looking at these points right here. So I've got secant x, right? And I've got y equals negative √2, which means that's happening at 3 pi over 4 and 5 pi over 4. So it makes sense that there would be 2 solutions between, well, what exactly are they asking for? They want, approximate solution of the equation on the interval from negative 2 pi to 2 pi. Well, let's take a look. So, negative 5 pi over 4, 3 pi over 4. So, 2 pi is right here. So those two solutions, 5 pi over 4 and 3 pi over 4 work. And negative 2 pi is over here. So I've got two other solutions at negative 3 pi over 4 and negative 5 pi over 4. So there's some weird symmetry such that all 4 of these are solutions. So when we're asked, the solution would be x equals negative 5 pi over 4, negative 3 pi over 4, 3 pi over 4, and 5 pi over 4. So as a matter of fact, between negative 2 pi and 2 pi, there are 4 distinct solutions. Okay, even and odd. Okay, so tangent is equal to sine x over cosine x. Now, to jog your memory, sine is an odd function and cosine is an even function, okay? Now, tangent itself, when you graph it, at least about the origin, looks like this, right? Okay, it's got the asymptotes and all. So it turns out that tangent itself is an odd function. So one way to tell, or a little cheat, or if you will, is that if a function has an odd function as part of it, it's going to end up being odd. Now, secant is related to cosine, right? So cosine, if you'll remember, is an even function, right? Cosine is an even function, which means when you look at secant, right? If you look at it, it's symmetrical about the y-axis, which means that secant itself is also an even function. So anything that's just related to cosine is going to be even. So if you can remember that cosine is even, it turns out that everything else, tangent, cotangent, cosecant, and sine are all odd. Okay? All right, last but not least, what we're being asked to do is, for this range of angles, and this is kind of important, we're at, so negative pi over 2, that's negative 90 degrees. So what they're saying is, like, this could be positive, and then this would be negative. What they're saying is you're facing the camera from here all the way to here, right? So that'd be negative pi over 2 to pi over 2. Now notice they're saying strictly less than, right? Meaning they're not including it, because technically you're never actually going to see the road. So if you sight this, what is this, a viewing platform, you're going to see the parade, right? Here's the parade, and yay, parade. There, that's my parade, whatever. It's going to do what? It's going to be very far away. It's going to get closer and closer and closer, and then right when it's right here, it's going to be closest, and then it's going to get farther and farther and farther and farther and farther away. So what they've done for a particular instance is provided you with a right triangle that you can write an equation for. So you got this right triangle, right, where this is 27 meters. This is the distance of whatever it is, right, the parade. So then what we can do is we can say, oh, well, there's our 90 degrees. So that's the adjacent, that's the hypotenuse. So we know that the cosine x is equal to the adjacent over the hypotenuse. Now, you can solve this because they want the distance d from the camera related to the, as a function of x. So they want d in terms of x, meaning they want us to solve for d. So if I do that, I'd multiply by d and then divide by cosine. So I get 27 over cosine x. By the way, that's the same as 27 times 1 over cosine x, which means that d of x could be written as 27 secant x. Okay? Now, if you think carefully about what secant x, 27 secant x looks like, graphically, the answer actually makes some sense. So this is the graph of 27 secant x, and I've just restricted the domain from negative pi over 2 to pi over 2. So you can see that this graph looks like that. And this point right here is 27, meaning at a 0 degree angle, looking right at it, 27 is closest, and as you go this way, it gets farther and farther away. And as it's coming in, it gets farther and farther away. Okay? So that's it for the examples.